Thank you everyone for inviting me. I'll be presenting OpenThoughts, which is a paper that I worked on for the past year. It's about how we build up reasoning models in the open, and this is that project. Thank you so much. So I'll just introduce reasoning for those who are unaware. I'm pretty sure everyone in the room is aware, but reasoning is kind of this paradigm that OpenAI introduced where you scale test time compute and you really get amazing benchmark scores. On these benchmarks that we previously thought were very, very difficult for LMs to solve, we suddenly saw very, very large gains like AIME and math, coding, science. It was really, really quite impressive, but we were unsure as an academia how to build these models. And you can kind of see when the reasoning paradigm kind of started. You see the general increase of benchmark scores over the past 5 years, and then at the very end, you see this large, large uptick in a lot of really important benchmarks. And this kind of coincides with the reasoning paradigm. So it makes very much sense that we want to reproduce this, and one of the very first papers to do so was DeepSeek R1. It was one of the best reasoning papers that come out. It kind of discussed how they trained their reasoning models, but again, their data was completely closed. It wasn't sure how they trained their model. They had some brief details, but again, the data for this process was completely closed off. And through this paper, actually, one of the most important things is that they demonstrated that small models could really reason quite well. So they released, alongside their R1 model, released 6 other smaller models that really perform really, really well, competitive with frontier models on these relevant benchmarks. So you can see on the right-hand side how we compare models like, distilled Qwen 7B against like O1 Mini, for example, or GPT-4o Claude Sonnet. It was very, very, very competitive, which is quite impressive and encouraging for open source community. And so the question is, okay, how do we actually train our own reasoning models? We care about, why would we do this? We want to, we want performance. We want to be able to control our own models. There's privacy of our data. There's improvements of latency. We have our own models. And actually, you control when when you're able to train your own reasoning models, you have ownership over that thing. You can control what you do with that. So it's quite a desired outcome. The very first paper to do so was this paper called SkyT1 that demonstrated that you can take 17K reasoning traces through SFT that you distill from Q to a Q, and you can really get really surprising performance actually. So if you take a Qwen 32B and you train on this like very small data set, you get performance really comparable with that O1 preview, which is really, really surprising. And so my group is the Datacomp group, and this work started with Ludwig Schmidt. His like kind of take is that datasets are one of the best ways to improve ML. It's been kind of the fundamental progress mover for a lot of the great things like MNIST and ImageNet and Web image text. And Datacomp is a project that kind of focuses on dataset building. So for the very first project was CLIP, so it built a big dataset for CLIP models, training CLIP models. Next one was pre-training language models, and the next iteration of this was training for reasoning models. So actually, our very first stab at this was a model called Bespoke Stratos 17K. So we wanted to take the SkyT1 pipeline, but we made a few tweaks to simplify it. So in the Bespoke Stratos thing, we changed the teacher. So they used Q to Q, we use R1. They had this rewriting step where we removed, so they rewrote the traces to make it more readable. We'd remove that. They did this complex regex and SymPy answer extraction. We swapped that for an LM to get better recall, give them some ground truth. And it's kind of the high level view of our pipeline. So we start with some data sets. We use our DeepSeek R1 to annotate. We verify using a couple of different methods, and we get this final 17K data set. So very much our reproduction, and with a few tweaks. And the downstream model was a good amount better over SkyT1. It was actually at the time still worse than the 32B Soda, which is R1 still 32B, but it was getting there. It was the best open source or open data model, I'll say. The very next question, okay, how do we build better? And the very next thing we did was make it bigger. So we made more data. So we created OpenThoughts 114K, which has included just more prompt sources. So we just took more questions. Very simple next iteration. And we used exact same pipeline. And this next model got called OpenThoughts 114K, really, really pushed up. It really got closer and closer to the DeepSeek models. We compared with existing datasets like General Thoughts and OpenR1, Neurotron, and it was really, really the strongest out of all of them. So the way we kind of scaled it up is evaluated a bunch of different question sources. So we just did this basic ablation of, okay, how can we compare code questions and math questions? So we did a large scale ablation of like 20 or 30 different data sets. And we just took the best question sources and mixed them. And that was what ended up being in our final mix. So this is the high level look of OpenThoughts 4 and 14K. And then the very next iteration is OpenThoughts 2, where we did this very next thing where we just scaled up even further. So we took even more code sources. We included OpenThoughts 4 and 14K, and we had this OpenThoughts 2.1M model or mixture data set. And it worked really well, became very popular. We actually caught up to R1 Distill 32, which is very exciting, through just very simple techniques, just scaling up existing methods and doing this ablation of question quality. It's very simple. But we still had a lot of basic questions on the table, like how much data do you need to actually get really good models? What curation steps are necessary in the pipeline? What are the best choices for each curation step? How do you actually figure this out? These are all like very basic scientific questions that we hadn't answered up to this point. And so we kind of, solve this, we kind of broke down the reasoning data pipeline into like 4 steps. First, you have to generate your questions or instructions. Next, you have to filter those instructions. Next, you answer those instructions using some sort of teacher, and then you filter those answers. So you can kind of see our pipeline for generating reasoning traces. We have to this pipeline doesn't cover everything, right? There's a lot of methods that don't fit into this pipeline, but for now, this is kind of a general enough pipeline that will catch most things. And so we use this pipeline to build OpenThoughts 3. And so as a sneak peek of our results, OpenThoughts 3 is the point of our paper. It's kind of our final artifact. It's a big data set that we really do good science to improve the data set quality. And you can see across multiple scales, it really is a data set across, competing with great data sets like Neutron Nano or an AM data set. And across all scales, it was really powerful in producing strong reasoning models. And here's a table demonstrating results. Actually, at the time, using the science we're about to do, this model, OpenThoughts 3.7b, trained on OpenThoughts 3, was the open source open data like soda. It was far outperformed DeepSeek's models, and it outperformed all other RL models at the time. This is a little out of date now. That there's some other in the last like month or two. There's some paper models that have come out that have surpassed us and building on top of some really great work. But at the time, this is the strongest. So let's actually get into like how we built this. So there's 2 things we scaled because we scaled dataset size. We also improved the dataset recipe. And so we're going to talk about that right-hand part for a lot of this, improving dataset recipe. So just a brief kind of go over our experimental setup. Since there's going to be a lot of experience I'm about to throw at you, all the ablations in this paper were the same specific data scale. They're all 31.6K data points. Unless I tell you otherwise, that the teacher for everything is DeepSeek R1. The training is absolutely fixed across everything. So we're using Qwen 2.57b instruct with fixed hyperparameters each step of the pipeline. So we're going to iterate through each step of the pipeline. So the 4 steps I talked about. And we'll start early in the pipeline and then we'll go towards the right. And as we do an ablation for a given step of the pipeline, we'll take the best strategy from that step and we'll keep it fixed throughout the rest of the steps. And we compare different strategies for each part of the pipeline using 8 different benchmarks covering math, science, and code. So the very first question we're going to answer is, okay, we're going to start with how we actually get our questions. So if an SAT data set's a bunch of question and answer pairs, how do we get our questions? So we can start with just ablating different generation techniques. So in this table, we have, we've looked at different ways of generating code questions. And the second way of different ways of generating math questions. And the third way of different ways of generating science questions. And there's a lot of different data sets that aren't included in here. So in this table, just for space reasons, there's almost 80 different ways of generating questions that we thought about and ablated. And you can see there's a huge spread in terms of the question quality. So even with the same teacher model, just changing how you find your questions makes a really large downstream impact. And things that you wouldn't expect come out in this table. For example, sometimes synthetic math questions performed very real math questions, for example, in Numina math. Things that like uh, like code golf, which is something that hadn't existed before, it wasn't really trained to our knowledge, was better than many other existing data sets that come out. These large scale projects. So this very simple way of finding questions, and there wasn't really a pattern like what was the best in terms of like the synthetic questions the best or purely real questions the best. It wasn't actually there wasn't a pattern. For example, for science, it was a combination of semi-synthetic questions and real questions that worked out the best. But for math questions, actually pure synthetic questions is the best. So it really goes to show you that there's a lot of science of like what type of questions win for SVD data sets, and displaying them and doing this large scale ablation really opened our eyes and just figuring out what really works. So, okay, now we have our set ways of generating questions. A very next question is, okay, how do we mix them? So we have like 80 different data sets, and we kind of ranked how we get the question from them. How do we actually mix them? And the very, very surprising thing that we found was the more question sources you have, so less the performance. So actually taking all your questions from one single source, the best source was really the best way. So for math and code, looking at the top one math sources was the best. And looking for science, taking the top two was the best, which is really surprising to us. We really expected coming into this that we're going to mix a bunch of different sources to maximize diversity, but it just didn't play out, which is, I think, is a super interesting thing we found just by doing very simple data science. Okay, so now we have a way of taking questions. So we have our question sources, we've mixed them, and now we have ways of getting questions. How can we filter down this question? So a lot of people in the literature have worked on, okay, how do we actually filter down uninteresting data or data that's not going to help us downstream evals? And in the pre-training way, people really think about like, okay, I'm going to use fast text models or embedding models, these very classical techniques. We kind of found the very, very odd thing is that GPT filters, like LM filters, worked really, really well. For example, the simple technique of annotating each question with like a very simple model like GPT-4o mini, and just taking the question that the longest response really was a really great filter, surprisingly great filter. And for code, the best filter is asking a model how hard this question was on a scale of 1 to 10 and taking the hardest questions. These really, really, really simple filters outperformed things like fast text or embedding based models, or these things are very much more classically recognized in pre-trained literature, which we really, really found was surprising. These simple things work so well. The next thing that we thought was really, really, really surprising, okay, is, okay, we have our ways of getting questions. How do we actually answer the questions? So right now there's some inherent way of getting questions, and we can either we can deduplicate them, right? Deduplication is a really, really common thing to ensure diversity in your data, right? If you have repetitive data, it makes sense that you wouldn't want to train on the same data over and over again. But you can also go the other way. Let's say we could actually ablate, can we add more duplication to our data by like repeating questions? So we kind of do this combinatorial exploration where we take different ways of doing dedupe, so exact dedupe, where we remove questions that are exactly similar to others in the question set. We do fuzzy dedupe where we use some sort of n-gram string matching to see, okay, if there's some that is a string there's a question that's similar to other questions in the data set, we'll remove it. And then there's no dedupe where we don't actually do any dedupe on the questions. And then there's multiple answer generation. So we take a question, so with 16x sampling, we'll take a question and repeat it 16 times and answer it 16 different times with the same teacher model. So the answers will be different 16 times. So all those 16 times the answers will be different, but the question is the same across. And we actually found that for all the domains, so science, math, and code, doing 16x sampling was the best technique. So actually repeating questions was the best way of getting performance, which was super confusing. We really expected, okay, you want a lot of diversity for questions. Literally repeating questions did not seem to be an intuitive thing for getting improvement, but it really worked out across all the domains. And actually it gives a really nice tool for scaling up data set size. So instead of having to come up with more and more questions, you can just repeat questions and answer them more times, which is a really nifty fact for doing scaling. We're going to get into it later. And actually, another funny thing that we found was that filtering those answers did not help. So in the literature for reasoning data, a lot of people really focus on verification. We might have wrong answers in our data set. It makes sense. We shouldn't train a model on those wrong answers. But no matter how we looked at it or how we tried, doing filtering on those answers, so like taking the shortest answers, removing non-English answers, using LM as a judge, using other filtering techniques. None of them beat the experiment of just training on all your answers, no matter training on all your data, no matter what. So just not filtering at all. This is true across math, code, and science. So we in our paper found that verification did not help at all with making better data sets, which is really, really surprising to us. And this is also one of the funniest things that we found. We across all of our experiments, we've been using DeepSeek R1 to create our data sets. But a very natural thing is, okay, we can change our teachers. There's a lot of different ways to create teachers. Maybe different teachers are better. And so we tried it, and we found actually Q was a better teacher than DeepSeek R1, despite QWQ being less performant on our benchmarks than DeepSeek R1. So using a weaker teacher actually got us better data sets, which is super, super surprising to us. We didn't expect this, and this really came at the very end, and we were really, really excited by this result. Okay, so how do these design choices stack? We can see across the different pipeline stages as we, at different scales, take our decision choices. So changing our question, changing how we mix the questions, filter the questions, change our teacher model. You can see that each kind of design choice kind of improves us, gets us higher scaling and better scaling, just changes the intercept on this curve. And we scale this up. So we've been doing everything at the 31.6K data question scale. We scaled up to 1.2 million scale to match OpenThoughts 2. So this diagram kind of walks us through the entire generation pipeline. So we have some source questions. So open math, code golf, open code reasoning, stack physics, and some organic chemistry questions. We filter them down using the best filtering techniques. We do the deduplication and the multiple sampling that we talked about using the 16x sampling. And we do generate multiple answers. We do the 16x sampling. And we get our final data set of 1.2 million question answer pairs. And how does this data set perform? Again, it was the SOTA open data reasoning model, which we were really, really excited by. There's a lot of great work in this area, and to be able to create something that's at this level was really, really exciting to us. And actually, the very great thing that we did was you might have, worried, oh, you may be overfitting to the benchmarks you're tracking. So the 8 benchmarks we're tracking throughout the paper and ablating across were these 8 benchmarks over here. But throughout the ablations, we held out 4 evals, so HMMT, HLE, AIME 25, and there's another set of LiveCodeBench. And we actually found that on these 4 evals that we didn't track at all, we got SOTA performance across 3 of the 4, which is really, really great for us to know that we weren't overfitting to some non-held out benchmark. And the data set we released was really, really popular for each OpenThoughts iteration. The data set was the most trending Hugging Face data set for at least a couple of weeks, which is really, really great. We got a lot of thousands of views. The model itself was super, super popular, and people really got great use out of it. And we now released the paper, the model weights, the data set, all of our code to generate everything to do the training and the data gen. We released our eval setup as well, and we're really, really happy with it. The paper again is right here. It was a huge, huge team effort. We throughout this project, we trained almost like 3,000 models and 3,000 data sets. So it was a really, really large cumulative effort across a lot of really talented people. It was a really great project. And this is the kind of a great infographic of the entire team. And I think I've just finished within time. So yeah, I think if anyone has any questions, I'd be happy to ask.
Thank you so much. What an interesting set of things you've identified as being important.
Yeah.
Really great usage of the data set. So I think to start with a question, the adding more questions and more copies of the same question is a very interesting result to me. How did you guys even think about using that as an approach?
Yeah, we were thinking about, okay, we wanted to try dedupe strategies. We were like, okay, how can we duplicate our questions? And we thought, okay, if amount of duplication is one scale, which we're ablating, like that's the x-axis, what if we just went further and actually manually duplicating? And we thought, okay, we should see this very nice ablation where the more duplication we have, the less the performance. And we actually saw the inverse. It kind of just went up the opposite way, which is how we came up with it.
That's very interesting. Another piece that I find interesting here when you mentioned that it was state of the art, and then you said, I don't know, in the last few weeks, there are new benchmarks. In this space of benchmark generation at this time in AI, can you provide your view of the speed with which benchmarks are being created? And I mean, it seems like it's very there's a lot of work that goes into creating one. And then if others come in and create new benchmarks at a pretty rapid pace, I'm just curious on your perspective on benchmark generation, the challenges of it, and what it looks like in the current age of AI.
Yeah, so I think the hard part about doing these like large data set projects is that like it's so computation intensive to generate something very strong. So we burn, we train so many models and we just we it's a large scaling endeavor and it's very hard, I think, in academia to do these large projects. And a lot of really great people spend a lot of great time just thinking about how do we do these things quickly. And of course, with the scale of AI and how fast everything's moving, it's really, really tricky to keep something that's lasting. I think, at least with this work, and I think a lot of other works that people have come out in the reading space, I think doing good science and actually building something that's n- not just a scale up of what's existed before, but really moves a wide intercept of improving the scaling curve at all for everything really is important. And I think that's where we what we tried to do. We kind of hope this serves as a basis or like a building block for others to build and better reasoning models or better models in general. And that's what we've kind of seen both some model release that there's been better data sets that have come out, but a lot of them are like based on something we did, or they've used some intuition, or they're maybe even mixing with our data set, which has really been really great to see. So, hopefully with doing just good science and building something as a building block for the rest of the community serves as a useful tool for everyone else.
I'll ask one last question. Throughout this work, you've identified a lot of interesting ways in which you've improved the data set quality. Do you have any bigger picture viewpoints from this effort about key components to creating quality data sets in general?
Yeah, I think the number one thing that I think we had to keep in mind was that the methods that might not have been perfect but scale really well, that means you can do them a lot, tend to just work out well in general. Like the methods of getting questions that scaled super well were great. So I think when we found questions of like we thought about different question sourcing strategies and we're like, okay, we want to like really look at textbooks. That was great, but it scales less than like other ways of getting questions, like really sourcing harder questions. So the things that just scaled better ended up working out better anyways throughout the thing. And so I think that was the most important thing that we learned was just designing your pipeline with scale in mind is a really, really helpful heuristic for designing better data pipelines.